Okay, so I'm going to do two problems today, and the first problem is going to be a compressor problem, but it has really tricky language in it, and I want to go over that really tricky language and help you understand what's happening. So a compressor, as you know, we draw it like this: the air is being compressed, the volume is going to get smaller, so we're going to draw it like this direction, and we're going to have states 1 and states 2, and we have a shaft here. And this shaft is saying that we're putting in power. We're putting in power into this compressor. And they tell us that we're dealing with carbon dioxide. Carbon dioxide, we're going to treat it as an ideal gas. Remember, carbon dioxide can be treated as an ideal gas, but those 5 things that we have steam tables for: water, ammonia, propane, R134A, R22, when they're in its gaseous state, we're going to look up those properties in those tables. We're not going to consider them to be ideal gases. Water, steam is not an ideal gas. Now, there is a little bit of confusion here because you will see water vapor in the ideal gas tables, and that confuses students. And so let me just tell you this right now. When your system is 100% gas, 100% water vapor, 100%, that water vapor does not act as an ideal gas. But right now in the room that you're in, there is dry air and there is water vapor in the room. You've evaporated, you sweated, there's just all sorts of humidity in the air. At that level, when water vapor is not 100% of the air, it is going to act like an ideal gas when something called its partial pressure is low. And maybe go back to chemistry. So that's why that water vapor shows up in that table, in table A23. But for right now, until we get to that, which is chapter 12, which will be the last chapter that we're going to discuss this semester, water is not an ideal gas. We're not going to consider it to be an ideal gas. We're not going to use that column in our table. So I know it's a little confusing. I'm just trying to explain what's going to happen there. Okay, let's look at this carbon dioxide again. State 1 and state 2. Okay, we know the pressure at 1 is equal to 20 psi. The temperature 1 is equal to 32 degrees Fahrenheit, and they give us a velocity of 1 is equal to 30 feet per second. So this is not, we are not going to consider that kinetic energy is negligible here because they gave us a velocity to deal with. Okay, the pressure 2 is equal to 50 psi. The temperature 2 is equal to 120 degrees Fahrenheit, and the velocity 2 is equal to 80 feet per second. So we're increasing by 50 feet per second, and that's going to be some kinetic energy change that we're going to have to look at. And they tell us the mass flow rate of the carbon dioxide is 0.98 pounds per second. And then they also tell us this statement, and they say the heat transfer from the compressor to the surroundings is 5% of the work input. Okay? This is the tricky wording, and we'll talk about this wording in a moment when we get to this segment here. So the other thing they want us to talk about, they want us to do this with a constant specific heat method. So they want us to say that the specific heat is going to be 0.21 BTUs per pound per degree Rankine. Now let's think about if this wasn't given to us as constant specific heat. Carbon dioxide is one of our table values in table A23, and that is given to us, the properties are given to us in BTUs per pound mole, not BTUs per pound mass. It's those gas tables are the one that's given to us in a molar state. So if we were to use our H values, we would give H bar for carbon dioxide, and we'd have to divide by the molecular weight of carbon dioxide to give us what the value of H is. So this is, we're going to be in this world here, constant specific heat, which in many ways is simpler, is easier. We don't have to do a lot of interpolations when we're dealing with constant specific heats. But we do need to we need to understand that this one's available for us. to use. Okay, so I want to do this. Okay, now we want to find this problem. We want to find the power in horsepower. Okay, that's what we want to find here. And so we're going to go through our equations that we know. The first thing, let's just start at the beginning. We know that the change of mass of the control volume with respect to time is equal to the summation of my mass flow rates in minus the summation of my mass flow rates exiting. I didn't tell you anything about this, but I'm going to say that this is a steady state situation. Carbon dioxide is coming in, carbon dioxide is going out. I'm just going to say it's steady state. All right, so this is going to go to 0. Again, there's going to be very definitive situations that are not steady state. This one is going to be steady state. And there is no summation here. There's just mass flow rate and mass flow out. So 0 is equal to m dot 1 minus m dot 2, or we can say that mass flow rate of 1 is equal to mass flow rate of 2, which is just equal to our mass flow rate, which we were given up here in the problem statement, so we don't have to worry about it. You can do this in your head. This is nothing spectacularly difficult, but we're going through the steps. Let's go through the steps to make sure we are complete. The next thing we have to do is go through our energy equation. So what's our energy equation? The change in energy of our control volume with respect to time is equal to the heat transfer rate minus the rate of work, plus the summation of my mass flow rates in times my enthalpy in plus my kinetic energy in, plus my potential energy in, minus the summation of my mass flow rates exiting times my enthalpy exiting, plus the kinetic energy exiting plus the potential energy exiting. Okay, again, we are going to be using this problem and this equation at steady state. So the properties are not changing with time. The property of energy is not changing with time, and that's going to go away. We don't have a summation here because we just have one mass flow rate going in and out. And we don't have any potential energy. They didn't give us anything about the potential energy, so this is going to go away as well. But they did give us a velocity. So we can make a decision about whether we're going to assume the velocity is negligible or not. And so because they gave us a velocity, right now I'm going to say I want to use it. And so we're going to have kinetic energy terms here. But now we have to figure out this thing. This is where it comes down to the wording. Remember what the wording said. The heat transfer from the compressor to the surroundings is 5% of the work input. Okay, let's look at this. The heat transfer from the compressor to the surroundings is 5% of the work input. What am I going to put in here for Q dot? I encourage you to pause the video. Just think about this. What would you do for Q dot? Okay. 5% of the work input. So I know that this Q dot should be 0, whoops, let me write this as 0 is equal to, the Q dot should be equal to 0.05. That's 5% of the work input. Okay, W dot. Now the question is, should this be positive or negative? What should I put there, positive or negative? Well, it's saying the heat transfer from the compressor to the surroundings, which is a negative value, is 5% of the work input. Well, remember, work input in thermodynamics is a negative value. So what we actually should do is we have it correctly as it's sitting right there. That 0.05 of W dot is going to be a negative heat transfer. Okay, because work in to a system from the surroundings is negative thermodynamically. All right, now we're going to have minus our other W dot. The other thing is here, we cannot change, we're putting in the variable W dot. We can't change how we're dealing with it in 1 or 2. We have to have the same sign for the variable. So that's important there. Okay. Think about that. That sometimes bothers people. It may bother you. It's okay if it bothers you. Let's think about it. Let's try to understand that, wrap our mind around this. Now we do the rest of the equation, plus m dot times h1 minus h2 plus v1 squared minus v2 squared all over 2. Okay, so that's what I have. And now I go down to my next thing. I'm trying to find out what the power is. I'm trying to find out what W dot is. Okay, so this here is going to give me negative 0.95 W dot. All right, or I can do this as W dot is going to be equal to, if I move this to the other side of the equation, it's going to be mass flow rate times H1 minus H2 plus V1 squared minus V2 squared all over 2. And I'm going to divide this all by now 0.95. Now again, here's where we would choose, if we were going to do variable specific heats, we would look up the H1 and H2 bar. We would find this as H1 bar over molecular weight, and this is going to be H2 bar over molecular weight. But that's not how we're doing it here. This problem is saying constant specific heats, and so I want to do it that way. Okay, so we're doing the ideal gas assumption, constant specific heats, and we're going to get to the power is equal to mass flow rate times C sub P T1 minus T2 plus V1 squared minus V2 squared all over 2. Okay, 0.95. And now what I want to do is, I have everything here I need. I'm going to start plugging in some numbers. Okay, so my power, W dot, is equal to 0.98 pounds per second. C sub P value is 0.21 BTU per pound per degree Rankine. Temperature 1 and temperature 2, I could convert them to Rankine if I want to, but I should know that the difference in Fahrenheit is going to be the same as the difference in Rankine, so I'll leave them in Fahrenheit. You can feel free to do whatever you like, convert them or not. This is going to be 32 minus 120, and this is going to be a difference in degree Rankine. My velocity change there is going to be 30 squared minus 80 squared divided by 2, and this is going to be meter squared, sorry, not meter squared, we're in English, feet squared per second squared. And we're going to divide this by 0.95. Okay, now, I want to, I'm just kind of doing this a little bit differently here, wonky. I'm going to just do some partial calculations. And I'm going to give them to you. You can type them into your calculator. You can pause here and type that into your calculator to make sure it's right. But I want to make sure my units are correct. I'm going to say I'm going to do an intermediate step here, then I'm going to check my units. So my first thing is going to give me, this is going to be negative 18.48. This is going to be BTUs per pound, right? Because my degree Rankine is going to cancel it, BTUs per pound. My second term here gives me minus 2,750 feet squared per second squared. Now I know I cannot subtract those two numbers, BTUs per pound and feet per second squared, until they have the same units. I have to wait. I have to do my units before I can even combine those together. So here's what I do for feet squared per second squared. And this is a technique you need to know. You need to know this technique. Just like I do for SI units, I'm going to say that a force of 1 pound force is equal to 32.2 pounds mass feet per second squared. In SI, I did 1 Newton is equal to 1 kilogram meter per second squared. But it's not that way in English units. Okay, so that gives me second squares go away. One of my feet goes away, and I have pounds force feet. I want BTU, so there my computer just started up. Sorry for I'm processing this video at the same time I'm making it. Takes some energy. I know I don't want pounds force feet. I want BTU. So I know that 778 pounds force feet is in 1 BTU. And now I've taken care of my unit issues. Now I have BTU per pound mass and BTU per pound mass. Okay, and now I can add those things together or subtract those things together in this case. What I'm going to do is I'm not going to add them together right now. I'm going to show you what they is. I'm going to show you what they is. I'm going to show you what that calculation is going to give you. Negative 18.48 BTU per pound minus 0.11 BTU per pound. Okay, all over 0.95. Question should be asked: the velocity change from 30 to 80 feet per second only took away 0.11 BTUs per pound. That's a pretty big change in velocity and a pretty small change in energy here. So we could have neglected it. We really could have neglected that kinetic energy change. But I just want to show you how you have to have a significant kinetic energy change for it to not be considered negligible. I mean, 50 feet per second is still borderline here. It will change our number, so we're going to deal with it. We're going to work with it, but not significantly. Okay. Here, W dot is going to be equal to negative 19.18 BTU per second, and it's good that that's going to be negative because it's a compressor. We're adding work from the surroundings into the system. It should be negative. That's good. We didn't want BTU per second in our answer. We wanted horsepower. And so we're going to say that there are 3,600 seconds in 1 hour. And then we're going to say that there are 2545 BTUs per hour in 1 horsepower. And this is all going to cancel out. BTUs, seconds, hours, horsepower. Our units are okay. And this is going to be a negative 27.1 horsepower. So the problem statement might say something like, what is the power required to run this compressor? Power required. They already know it's negative, and so I put in the magnitude, 27.1 horsepower in my answer. If they don't ask me in the problem statement that way, if they say, what is the power for the compressor, I'd have to put negative 27.1. Okay, but if they say something about required, or they say something about produced, then I wouldn't have to do a sign convention, because produced tells me they know it's positive for a turbine. Required says they know it's negative. Okay, so that is our problem there. That is our problem number 1. Took me about a little bit of 17 minutes to work on. We will get you out here a little bit early. Maybe not as early as what I was hoping today, but I will work on another problem and talk about that in our next segment.